Hello everyone, welcome once again to Economics. Now today we are going to be starting with the concept of Taylor series, just a continuation of what we started about two classes ago. So um, now, like I said in the first class, I said Taylor series is just more or less like a twist to the Maclaurin series, just a simple twist to it. It's not really that different because as you will see, we are still going to be applying that same Maclaurin formula to explain the Taylor's formula as well. So now, from the definition, this Taylor series involves expansion about any point other than zero. Now, you recall that from Maclaurin series, said it has to do with the expansion of um, a function around a particular value, and the value in this case is zero. But oftentimes we might encounter a situation where we have to expand a function around a value that is different from zero. So in such cases or instances, this method, Taylor series, helps us deal with that. So now, let's say for instance we have now this in this look at this, s equals s naught plus beta. This is a Greek letter, beta, right? Yes, that's a Greek letter, beta. So now this s naught it symbolizes what that value we wish to expand around. No, this is the value. This symbolizes the value we wish to expand around. Why this is the value we actually expand around, and this is like the deviation. The beta here stands for the deviation, like the deviation away from the exact value that we have to expand around. Now, the value s naught, this s naught is fixed, it is known. This is the deviation. So meaning, because this is the deviation rather, it means it varies from one particular function to another. Now, because x is fixed, s naught is fixed, this one is variable, so it changes from one function to another. So, and that's why here it's a function of this. So in this case, let's represent that with this g of this. Now, we are going to be working with the simple equation that we worked with in our first class, which is this simple quadratic function worked with in our first class. So now, here what we have done simply is to substitute what we have here into the function. So here has 2 plus 4 and this plus 3 and this again into now, which is equivalent to this, because we have established here that this is a function of this. So now, taking the derivative, so we are following the same process just as we have done for, or just as we did for Maclaurin series in the first class. But here, the only difference we have here is that there's a deviation. Zero is no longer the value, but it could be any value. So, and here the beta here symbolizes that deviation from that actual value. So now here, the first order derivative is this. So from this function, to differentiate this function, here you have here differentiating, because this here stands for x. So it's more or less like you are differentiating the original function we worked with in the first class, which is f of x. So that you are differentiating that original function. So this stands for x, so it's like you are differentiating this with respect to x. So here you have, for the first one, you have this 4 plus, then this reduces to this. Now, taking the second order differentiation, we have this as our result, which is equivalent to this. Now, if we are to expand this, now let's assume that that's our deviation, which we call beta is 0. So meaning, in this case, there's no deviation. So meaning the value we wish to expand around and the value we eventually expand around, they are both the same. So there's no deviation. That means we have the exact value. So in that case, we are applying the same Maclaurin formula here. is just a substitution of new variables here. The deviation here we have beta, but in the case of the original Maclaurin formula, you recall that we have x instead of beta, it was x. But now because of the deviation, we are just replacing that with beta. That's just what we're having. So now, in this case, because, like we said, deviation is zero, meaning um, there's no form of error, no deviation. Now, another way we can write this in form of the Maclaurin formula is to have something like this. So now, like we're saying, if this is zero, it means there's no deviation, and then this is the result of what we have from here. So now, expressing, if you are to express this our function, which is the function of our deviation that we have assumed to be zero now, if we are expressing it in terms of the Maclaurin derivatives, and you recall when we were treating Maclaurin series, we used these derivatives to represent the coefficient of the coefficient in the general function we assumed, which was the nth polynomial function, nth degree polynomial function we assumed. That was in the class. So now here we are expressing this function of beta, which we have assumed to be zero here, in terms of those Maclaurin derivatives. Now the formula now becomes, this is what the formula becomes. Then after that, here, this first term, you recall that formula we used in the last class. Here, this is the original function, for the original function, then this is the first derivative value. Now here is this represents the deviation. So this equals the deviation. This is let's say this is the value we wish to expand around, and this is what we eventually expand around. Now the deviation is represented with this. So now this stands for deviation. Now, just following the same pattern, here this is raised to the power of 2 here, because here is the second order derivative value, and that's it. So it's more or less like the um, the Maclaurin formula, but now with a little twist, because here we are introducing a value which stands as a deviation, and that's basically what we have. So now we'll move to, like, to see how to handle functions that are not polynomials, that are different from polynomials, how to use the Taylor series basically to handle such functions. Because in that case, we are going to be having a remainder. So because in the case of polynomial, because this Maclaurin and Taylor series are devices, like I said in the last class, they are devices that transform all functions into polynomial form. So they are usually in polynomial form. So when you are dealing with polynomial functions, they are usually, the approximation they give are usually exact. But in the case of non-polynomial functions, at times you have, like we did in the last class, there was a complex problem we solved. That was in the last class. The one involving a square root. That one is not polynomial. It's just an arbitrary function, but it's not polynomial. In that case, we realize the result of our result wasn't exactly the same as the question. So it doesn't give exact match in such a situation. All right. All right. So finally, we are going to be looking at the expansion of an arbitrary function. So now here we are going to draw on a mathematical proposition which is called the Taylor's theorem. Now, Taylor's theorem says that given, let's say, an arbitrary function, this is an arbitrary function, a general arbitrary function. The form is not specified in this case. So, given an arbitrary function, now if we know the value, of x, and the value is known, and the value of derivatives at that particular chosen value is also known, then an expansion is possible at that value. That's basically what the theorem says. So you have a particular arbitrary function. If you know the value of at which that of that particular function and the value of its derivative. You can see here we have the series of orders of the derivatives. And this is order 1, 2, and so on like that. And then it means the expansion is possible at that point. Now looking at this. This is just similar to the Taylor's formula we just derived. So here, just following the same thing, but in this case, we are representing with another Greek letter here. So here, in this case, we are representing with another Greek letter, which is phi. Yes. So it's still the same thing. But here, what happens is the only difference between this and this is that here we have a remainder term. So this says, okay, expansion about a particular function that is not polynomial will leave a remainder. So in this case, this is a remainder term. And here, this term in brackets, the one in brackets, and this is the expansion of the original function. But in case, let's assume now the situation where there happens to be a remainder, we'll have this term. So this is the sum of the expansion of the original function, which is this, and then the remainder term. So that's Taylor's formula with remainder. So in a situation whereby, okay, let's now assume the value for our n is 1, for instance. If the value of our n is 1, so here, if you substitute the value of n here, what do we have from here? The value of n here will mean, okay, we are looking at the first order of this Taylor series. That's the meaning. N equals 1 means we are looking for the first order, and that will mean here this, and so the first order will be this, and what you have here. Okay, sorry. The first order derivative here will be these two first terms in your in the approximate as I put it. This n equals 1 here stands for the order of derivative. So in this case, first order, that means, this is what I mean. Here we have okay, we have this equals this, the first one here, plus this n plus the remainder term. So now this is just now to determine the number of terms or the order of a particular series, whether it is Maclaurin or Taylor, is a formula here that is a simple way to actually determine that, and that's just n plus 1. This plus this will tell you the number of terms you will have. So if you are giving this to be 1, it means you are going to have 2 terms. So in this case, here we have just 2 terms in the polynomial function. And in a situation where the n is 2, let's say in a situation where n is 2, it means that you are going to have 3 terms. That is this, this, and this. That's that. All right. So let's take a look at this example on Taylor series. Now, the question says phi is into s is this. So this is the function. Now we have to expand around this. Now this is the chosen value. Now in this case, you notice here that the s naught is 1, is not 0. Now when we looked at Maclaurin series, I made it clear that Maclaurin series has to do with expansion around 0 as a value. So 0 is the value that functions are the Maclaurin formula is used to expand. Now, in this case, you have a value different from 0. and in this case it is 1. When we started this class, when we started the concept of Taylor series, I introduced a concept term. I called it the deviation, a deviation. So there's a value different from 0 now. So in this case, this value is 1. Now with n equals 4, here the n equals 4 here will mean the 4 order of derivatives. That means we are going to have 4 orders of derivatives. I hope you understand. So now let's just go into it. Let's dive into it. Now here we have, let's start with the first order differentiation of our function, that is, so what do we have here? Looking at this function can be rewritten as, okay, sorry, I think I'll quickly have to rewrite the question. I'll have to rewrite the question. Okay, so we have this. Now we can write this function as this. Alright, so now the first order differentiation is, now here we are going to apply the power function rule again. We are bringing the term within the bracket, we differentiate the term we have within the bracket. So, and that is 1. The differential of x is 1. Then this denoting product. Then here we have differentiate the original function. This comes forward. Then we have, so in that case, we have minus 1 plus x to the power of minus 2. The second order is okay. And the second order of this is, we are differentiating this again the second time. So that's what we have within the bracket at minus, that's 1. Then this comes forward, we have minus 1, minus 2. Then the original function, the original entity, which is this. Then here we have 2 in bracket 1 plus x raised to the power of minus 3. Now, the third order differentiation is, so again we are differentiating this. So we have 1 s minus 3 1 plus x raised to the power minus 3 minus 1. So we have minus 6 1 plus x raised to the power of minus 4. Now, the fourth order is, so we are differentiating this again the fourth time, and that's term within the bracket. Then I have minus 4 minus 6 1 plus x minus 5, and that becomes 24 4 times 6, this is 1 plus x minus 5. We are done with our differentiation. Since here we are given the number, total number of derivatives to be 4, the total number of terms here to be 4, the order of differentiation to be 4. So this is the last derivative we're going to have. So now the next thing is to insert, because here we are giving our value for x to be 1. So substitute wherever you have x, you substitute 1, and then so in the case of the first order uh, derivatives here, so that here the starting one here, we have from here, this is minus 1, 1 plus 1 to the power of minus 2, that is minus 1, 2 raised to the power of minus 2. So that is minus 1 all over 2 raised to the power of 2, and that is minus 1 over 4. Now, for the second derivative value, so for this, we have, we insert 1 again into our result here, and then we'll have 1 plus 1 to the power of minus 3. So we'll have, that is 2 raised to the power of, so this becomes 2, and that is 2 all over 8, which can be reduced further to 1 all over 4. Now the third, so substituting 1 into our third order derivative, we have minus 6, 1 plus 1 raised to the power of minus 4. So here we have minus 6, 2 raised to the power of minus 4. So we have minus 6, 1, 2 raised to the power of 4, which is minus 6 over 16. So this can be reduced. This 2 in this, 2, 2 is 8. This 1.
No. 2 and 6 is 3.
Sorry. So that's minus 3 over 8. And then for the fourth order of derivative here, we have 24, 1 plus 1. So we have 24. Okay, let's have it this way. Right, so here we have 24, 1 over 2 raised to the power of 5. And we have 24 over 32. So here we have 8 in this, 3, 8 here, 4. So that will be 3 over 4. So now let's write out our formula. So here, since we are dealing with, so here we are going to have 5 terms on the right, including the original function itself. So like when I introduced the Taylor series, I mentioned that to determine the total number of terms that we have on the right hand side of the formula, Taylor's formula, there's a simple formula you can apply, which is n plus 1 to determine the total number of terms. So n plus 1 will be, okay, we have, here we are giving 4 as n. 4 plus 1 means that on the right hand side you're going to have 5 terms. That means including, aside the 4 derivatives we have here, we're also going to have the original function itself. So this is what I mean. Have this here we have our then plus second order this square plus the third order and that is 3 use the power of 3 in the fourth order to avoid any form of confusion. Let's use the actual figure, which is 4. Now to the power of 4. Then lastly plus, in this case do not forget to introduce the remainder term, because in this case the function we are dealing with here is not a polynomial function, it's an arbitrary function. It's a function different from a polynomial function. So it's very possible we are going to have a remainder. So it's not going to be an exact approximation. So you need to leave the term, the remainder term. Alright. Oh, alright. And that reminds me, I've been talking about polynomial function. I've been saying that all over and over again. Now, I want to believe we know what is meant by a polynomial function. And if you don't, a polynomial function, polynomial simply means, another word that can replace that is a multi-term. Like you have a function with degrees or varying degrees. Like a polynomial you can have a polynomial of just 1 degree. In that case, it will be a linear equation function. If it's of 2 degree 2, it will be a quadratic. If it's 3 cubic and so on like that. So it's a multi-term and has varying degrees. So all right. So now from our results here, we have to start substituting values and then simplifying the whole expression. So now in the first case here, for this, we haven't gotten a value for this yet. The original function, our original function is 1 over the question we solved. This is it. Now, if we insert 1 here, we have 1 over 1 plus x, we have 1 over 2. So this first value here will be 1 over 2, which is the original function itself. Inserting 1 in the original question we are given gives 1 over 2 as the answer. So now now from here, this is 1 over 2, because this automatically is 1. So this is 1 over 2 plus this prime 1. The result from here is minus 1 over 4 x minus 1, then plus here prime 1 over 2. So from here we have this to be the result for this. So that's 1 over 4 over 2 times 1. 2 factorial is expressed as this, and squared. Then the third term there is from here, the result is this. So substituting it here, we have minus 3 over 8 all over, expressing the polynomial, the 3 factorial. We have this, then this is the power of 3, and lastly plus This from here is 3 over 4 over 4 times 3 times 2 times 1. We have x minus 1 plus a remainder term. Alright, so let's simplify this further. Here we have 1 over 2. Here, opening the bracket with this, we have minus 1 over 4x plus 1 over 4. Then here, this becomes 2 plus, this is 2, and then this expression becomes 1 over 4 times 1 over 2 here plus this from here becomes this is 6, and this becomes 6 plus, so from here 4 times 3 times 2 times this is 24, and this becomes don't forget to include the alright, so here we bring this here. This is without the variable, so we'll bring it, collect the like terms. So this becomes this plus 1 over 4 minus 1 over 4x plus this times this becomes 1 over 8 x minus 1 squared. Then here this becomes minus, this cancels this out. Here we have 2, and this becomes 1 over 16 r is to the power of 3 plus this here 1, this and this is 8. Then we have 1 over 32 bracket x minus 1 raised to the power of 4 plus the remainder term. Alright, so from here, I think all we have to do is, don't bother about expanding the bracket. All we have to do from here is just add this together. So by adding this, what we have, this is 4, the LCM, and that will be 3 over 4, n minus 1 over 4x plus 1 over 8 power of 3 plus 1 over 32 x minus 1 raised to the power of 4 plus our remainder term. This is the final answer. So in this case, you are expected to leave it this way. So that is the final answer. Alright, so in the next class, okay, I don't know if you have, from what we have done so far, I don't know if you have 1 or 2 questions to ask. So if you do, please feel free to drop your questions in the comment section. And also, in the next class, we'll be taking more questions on, maybe 2 or 3 questions on Taylor series.